So the last piece we want to talk about when we talk about correlation is a lot of fallacies or myths that arise from all this discussion about correlation and causation. And this is something that you see time and time again in the media, time and time again in just daily interaction with statistics, is the misinterpretation of statistics because of these beliefs. And the number one thing I see most of the time is this first one, is that correlation, it's like rule number one, is that correlation does not imply causation. Just because it appears that there's a relationship between the two does not mean that one causes the other. For example, this is actually this website I found actually just now when I was putting this together. So this website is here if you want to check it out, and I'll link it in the description of this video. But here is a chart, and instead of showing it as a scatter plot, they've shown it as two line graphs. Comparing the divorce rate in Maine with the per capita consumption of margarine, and it certainly looks as though either a lower consumption of margarine is causing a lower divorce rate in Maine, or a lower divorce rate in Maine is causing less people to consume margarine. This is ridiculous, obviously. The divorce rate in Maine is not impacting the consumption of margarine and vice versa. But there's an extremely strong correlation here of almost 100%, that these are linked. So there's a correlation here, but there's in no way are these causing each other to have this relationship. So correlation does not imply causation, ever, ever. You can show that a causal relationship is correlated, but just because it's correlated does not in itself imply that there's a causal relationship. You have to prove that causal relationship separately. The other idea is that correlation is only linear, and this is not necessarily true. That product moment correlation coefficient that we discussed earlier in another video is for only linear relationships. But as I said when we were kind of going through our calculator, nonlinear regression functions can also have a measure of their association and their strength. So I'll just say that nonlinear regressions also have quantitative. I'm just going to abbreviate quantitative measures of strength or of correlation. Usually this is shown by r squared, and r squared is such that r squared falls between 0 and 1. So if you're considering using a different type of correlation, regression, you still can quantify the strength of the association. Lurking variables is another big one, and it actually kind of goes along with correlation and causation. A lurking variable just refers to some sort of extraneous third variable that causes the relationship to exist. So it's not these two variables themselves that are causing the relationship. There's no directly causal relationship between x and y. It's some third thing that's actually causing this relationship to appear. So from the same website, here's a line graph. And again, they didn't show it as a scatter plot as maybe I would have liked to. But comparing the total revenue generated by arcades and the number of computer science doctorates awarded in the US. Well, these don't directly impact one another, even though the correlation is extremely high. Right? Arcades making more money is not directly itself causing colleges to hand out more computer science doctorates. What might actually be causing this is maybe if more people are playing in an arcade, they're getting more interested in game design and the way computers work, and that's going to inspire them to go off and pursue a degree in computer science. So there's this third variable, this lurking variable, and that's just the growing interest in computers in game design. That's encouraging people to go out and get these doctorates in computer science. So this is what I mean by correlation does not imply causation ever, right? These things, actually let me stay here, these things are correlated, but they themselves don't cause each other to change. There's something else in the mix that's actually causing this relationship to be correlated, and that's what I mean by needing to prove the causal relationship separately from the correlation coefficient. That's all I'm talking about when I'm talking about that. This next one is spurious or artificial, it's the synonym, mathematical relationships. What this comes down to is there an actual mathematical relationship that already exists between the two pieces of data? Between X and Y. For example, if you compare calories eaten at dinner with calories consumed total per day. Whoops. Calories consumed per day. Obviously, one already impacts the other because the calories you eat at dinner is a subset of the calories you consume during the day. So obviously there's going to appear to be some correlation because one is already part of the other, one is impacting the other. The other one you might look at is if you were to talk about a table converting kilograms to pounds. Well, there's already a mathematical relationship that shows that, so obviously it's going to look like there's a correlation because one is already related to the other. We know there's already a relationship there. We've got a linear relationship that already proves that it works. So we don't want to conclude that there's correlation or an association if something else is already mathematically justifying the connection. These last two have to do with just good data sampling. So use of separate populations. You don't want to sample from two separate populations. So if I have like group A and group B, and I want to compare height versus weight, the one thing I'm not going to do is take A's height and B's weight and try to compare the two. Right? That doesn't make sense because obviously there's no correlation between what one group weighs and how tall the other group is. The best thing to do would be to take the height and the weight from the same group. So use data from the same sample in bivariate data. Bivariate data. And poor sampling methods. Your data collection methods can influence your correlation in your statistical analysis, which is kind of what, I can't spell today, which is kind of what we've been talking about all chapter. Analysis or correlation. Right, I want to make sure my sampling is unbiased and I want to make sure it's a representative subset of the greater population because I'm drawing conclusions from this sample about the greater population. So I always want to make sure that my data collection has been done faithfully and it's been done in an unbiased way to make sure that I have the most reliable data possible in order to minimize the bias in my interpretation. So all 6 of these are things that we see time and time again when people try to interpret statistics. So we always want to be on the lookout for this when we're doing analysis or interpretation on our own and based on what we see ourselves. So we always want to be careful.